semaphores. If you know how to use a semaphore, semaphores becomes the robust and sophisticated tools to predict critical section. But if you play with the semaphores, if you don't know how to use the semaphores, obviously they are going to make your life very miserable indeed. So what we just need to do is, we need to confine to the framework of the semaphore, and we just need to follow the instructions carefully to use those semaphores. So that's it when you start talking about a semaphores. That is, we should not wrongly implement the semaphores. We should be able to implement the semaphores in a correct approach. Then the semaphores are going to make our life very simple, since the total critical section problem will be solved on the fingertips. So let us enter and dive into the topics of the semaphores. So before I take you people into the world of the semaphores, please like and share the session and subscribe to this channel if you haven't already yet. So mark your presence and who are here, who are with me right now. Let us start. This is all about my experience. So this is my Telegram channel. Once again, most of people, they are requesting me to provide with the Telegram channel. This is my Telegram channel. You just can follow and join my Telegram channel. If you do have any doubts, you can share directly in my Telegram channel. So let us start the semaphores. The thing is, so far what we have discussed, till now, we discussed about various solutions to protect the critical section. For that, we started analyzing with the Peterson solution, right? We started talking about the Pete's solution, which is the Peterson solution. This Peterson solution, of course, it is very robust, but it is not implementable. In the modern days architecture, it is highly impossible to use Pete's solution, since Peterson solution has a drawback that it cannot work on the modern days architecture. Then we analyzed one more way to protect the critical section, that is disabling the interrupts. The second one what we analyzed is, we analyzed disabling the interrupt solution. Of course, disabling interrupt also works pretty fine, but when it comes to the multi-process system, you cannot implement disabling the interrupts at all. Disabling the interrupts will never work on a multi-process system, but we don't know on which system our application is going to run. It could be either a single process system or a multi-process system. So we don't know on which system our application is going to run. So we cannot protect the critical section neither by Peterson solution nor by disabling the interrupts. Then we went for what you call hardware lock, TSL or compare and swap. TSL is a very good tool, but only the problem is it is inaccessible for the application programmers. Yesterday I discussed why it is inaccessible for the application programmers. Since application programmer has no idea on which processor his application is going to run, but he has every idea on which operating system his application runs. So rather than using TSL, if operating system provides you with a mutex locks, you will be able to use the mutex locks to protect the critical section. But mutex locks has the slightest disadvantage. Slight disadvantage. Of course, the disadvantage which you find in the mutex locks is also, can also be found in TSL and Peterson solution. That is busy waiting. What is busy waiting? Let me start the concept of the semaphores exactly from the busy waiting. When a process has to wait on a lock, when the lock is not available, a process has to get caught in the while loop. When it is caught in the while loop, obviously CPU clock cycles will get wasted. After all, being a designer, no matter what kind of a designer we are, if we are a designer, either you are a software developer, a hardware designer, our main motto, main objective is to protect the critical section, right? Yeah. Hi Harshita Anand, hi Anu, hi Chitra, hi Krishna. So very good evening one and all, and very happy to see you back. Yeah. Now, see, if you have any doubts, shoot it right now. I just want you people to shoot immediately whenever you got a doubt. I do not want you people to have any doubts right after we finish the session on the semaphores, on any synchronization tools. Right after we finish the session, let me admit for one more time. Okay. So any doubts? At that time, instantly you shoot it. I will resolve, then only I will go to the subsequent topic. Now, any of this, we found one difficulty, that is busy waiting. What is busy waiting? Busy waiting meaning CPU clock cycles are being wasted. We cannot afford CPU clock cycles to be wasted. Fine, infinite loop, infinite while loop is the busy waiting. Very good, Krishna. Yeah. Now let us understand what is a semaphore. Semaphore, let me tell you, semaphore is not a biggest deal. It is not as complicated as test and set lock or compare and swap, are not as complicated as even mutex lock. Semaphore is a simple guy. Semaphore is a simple integer variable. Other than that, you don't need to understand much about a semaphore. Semaphore is a variable. Semaphore, that too, it is an integer variable. What is an integer variable? Integer variable is an integer variable, can take any integer value. Okay. Now within the semaphore, when you talk about a semaphore, you need to talk about a few things. The semaphore S, whatever you say, when you declare a semaphore S, the semaphore S, the initial value should be equal to 1. If you are a programmer and you want to use a semaphore, you need to define an integer variable of a type semaphore. I will talk about this design part. Initially, it's an integer variable that must be initialized to 1. Okay. Right after the initialization part finished, that is, as the semaphore initialization part, that is, as the semaphore has got initialized to 1, right next, you won't be able to access the semaphore directly. You will only be able to access the semaphore by using two functions. One is wait and one more is signal. Rather than calling it as a functions, I would call it as an operations. Why? I will tell you later. Rather than calling it as a function, I am calling this one as an operation. I will only be able to access these semaphores right after the definition, right after the initialization, by using only two operations. One is wait and one more is signal. Wait can also be called as P, signal can also be called as V. As simple as that. So let us talk about the initial definition of the semaphore. Here I am expecting some doubt from you guys. Right after I finish the initial definition of the semaphore, you should ask me one doubt. I am expecting that. Sitting at your place, thinking that I am at your place, keeping myself in your shoes, I may throw a doubt right after I hear something from my class. So I want you people to be alert and I want you people to ask me that doubt. Let us see whether you ask or not. Semaphore S, what is this? It is an integer variable. Then can only be accessed via two indivisible operations. Sir, what is indivisible? Indivisible is atomic. I will talk about this atomicity, how atomicity will get implemented in some time. So semaphores can only be accessed by two operations. One is wait and one more is signal. Other than that, if you simply want to either decrement or increment, if you want to use the semaphore variable in some other operations, it is not possible. Semaphore can only be accessed by using two methods, two operations. One is wait and one more is signal. Originally also called as a P and V. P is equal to wait and signal is equal to V. Now, let us have a look at the definition of the wait operation and a signal operation. Are you with me? Are you with me? Yeah. Krishna, Chitra, Harshita. And anybody else? Chanchal. Hi, Chanchal. Now, look at the definition of the wait operation. When wait operation is being performed, any process which wants to check the value of the semaphore will perform a condition checking. It is going to check if the S value is less than or equal to 0. If the S value is less than or equal to 0, it will be caught in the while loop. That means that if the semaphore S value is equal to 1, that means that nobody else entered into the critical section. Semaphore S value hasn't been accessed at all, hasn't been modified at all. S is equal to 1, it is available. You will be able to enter into the critical section. S is equal to 0. No, it is not possible for you guys to enter into the critical section since S has already been consumed by somebody else. Okay. So initially any process, before it enters into the critical section, it needs to check if the S value is equal to 1 or not. If it is equal to 1, it will be able to enter into the critical section. How? Let us closely observe how wait operation is designed. In wait operation, initially, any process which want to enter into the critical section needs to check the condition. If S is less than or equal to 0, if it is so, that means that the semaphore S has already been consumed by somebody else. So it will be caught in the busy wait. It will be caught up in the while loop. Otherwise, it will be able to come out. Initially, first process, S will definitely be equal to 1. Then it will be coming out of the while loop. It will be released from the while loop. Right after it comes out of the while loop, it is going to decrement S. What is S now? Right after the decrement happens, S will become 0. Right? So obviously, for the first process, S value will be equal to 1. Then, first process will be able to enter into the critical section. Okay? And then, right after which, when the first process finishes its execution, it needs to leave the critical section. At that time, it will increment the semaphore S++. It needs to perform signal operation before any process leaves the critical section. Rather, let me correct, right after any process successfully finished with its critical section, it needs to execute one signal operation. In signal operation, simply, it will perform S++. So, this S value will become 1 again. Any process which is caught up in the while loop can be released and can enter into its critical section. This is a very simple definition of the semaphore. I mean, understanding the definition, simple definition of the semaphore, we don't have any troubles whatsoever. We'll be able to understand the solution, rather, the wait and signal operations very easily. Any difficulties in understanding wait and signal? I want you people to participate. The Harshita or Anu increments value. Yes. Any doubts so far? Any doubts so far? Anu, where are you? Chanchal, where are you? Krishna, tell me, do you have any doubts so far? Because I'm going to take you people to the next step here. Am I audible? Am I visible? Are you listening? I'm waiting. So as I don't have any doubts there, I feel that it is so far it is fine. So I'm taking you people to the next step of the semaphores. Let us focus on the wait and signal definition of a semaphore. The wait, especially when you talk about the wait, still it is not free from the busy waiting, right? Yes or no? Anu, hold on. I will talk about negative value. I will talk about the negative value, but not right yet. Okay? Let us understand. If you actually can focus on this wait operation, you can clearly see still there is a while loop. Still there is an infinite while loop. When a process finds that S value is either less than or equal to 0, a process will still be caught up in the while loop, right? That means that it is not completely free from the busy waiting. Of course, the busy waiting, what we have observed in the other solutions, is still persisting also in the definition of the semaphore, that is in wait operation. Am I correct or not? Yes or no? See, so why we are using semaphores right now? So far, whatever we have discussed is suffering from one biggest problem when it comes to the throughput of the computer system, that is busy waiting. So as all the solutions are suffering from the busy waiting, we want to go for a solution in which we can avoid the busy waiting. But when you look at this wait operation, still there is busy waiting. Yes or no? Semaphores are also not free from busy waiting. Am I clear or not? Yes, busy waiting is still there within semaphore. So what is the use? What is the difference between semaphores and the other solutions? So, understand carefully. These are not the final definitions. To make the semaphore simple, we need to go through the standard definitions. These are the standard definition of the semaphores. Now what we need to do is, we need to upgrade these definitions to next level in such a way that busy waiting can be completely avoided. These are not the final definitions. Wait and signal operations can be defined in such a way that the busy waiting can completely be avoided. Got my point? So, let us get into the usage of the semaphores. When we enter into the usage of the semaphores, let me admit something. We can have three different kinds of semaphores. Of course, when you actually classify, there are only two types of semaphores. One is the binary semaphore and one more is a counting semaphore. There is a counting semaphore, there is a binary semaphore. What is counting semaphore? Let me tell you. Are you with me or not? I want you people to be completely with me because semaphores, important topic no matter. It is not just for GATE. It is not just for your university exam. Tomorrow you are going to develop an application using the semaphores. For that, this is an important session, let me tell you, let me admit. If you are fine here, you'll be a best software developer, let me admit firmly. So, what is the counting semaphore? Understand carefully. The counting semaphore can be initialized to any value, some unrestricted domain. Just a short while ago, I told you that semaphore S value can be initialized to only 1, right? But if you talk about the counting semaphore can be initialized to any value. The value can be 20, the value can be 30, the value can be 100. Sir, what is the difference? Simple. The counting semaphore is used to protect the access to some instances of a single kind of a resource. There is a class of a resource. For an instance, there is a class of a resource printer. Okay. There are a total of 20 printers in the system. 20 printers connected to the system. So, I will be able to provide access to these printers for 20 different processes. 20 different processes can be able to use 20 printers. So, before accessing any of the instance of the printer, the process must have to perform wait operation on counting semaphore S. Let us say counting semaphore, I would say COUS. This is counting semaphore S, which is initialized to 20. Before any process uses one of the printer, it needs to perform wait operation. Wait operation decrements obviously, right? So, at max, we'll be able to provide access to 20 processes simultaneously. Right after all the 20 processes, all the 20 printers within a system got exhausted, that is that they are being used by different processes, this counting semaphore will become 0. So, no more process will be able to access. Let us say there is 21st process, want to access one printer. It needs to wait since semaphore value is not available. I hope it made every sense, right? Yes or no? I hope you got the point. So the counting semaphore can be initialized to some unrestricted domain. But a binary semaphore should only be initialized to 1 since the binary semaphore is just used to protect a critical section. That's it. Other than that, we don't use the binary semaphore for anything else. It is primarily designed to protect a critical section. Simple. I hope the counting semaphore and the binary semaphore, you got differentiated, right? Yes or no? Fine. Of course, binary semaphore, at the simplest definition, this is equal to mutex lock. Yesterday we discussed about a mutex lock. Binary semaphore, as far as the normal, general definition is concerned, it is not different from the mutex lock. Anyhow, we don't need to discuss about the mutex lock. Let us completely focus on the semaphore. Okay. Now, can solve various synchronization problem. Now let me tell you. The semaphores can also be used to synchronize two processes. Let us say there are two processes must be executed one after another. For an instance, there is Krishna and there is Chitra. First Chitra must execute, followed by Krishna. Okay, there is a process Chitra and followed by Krishna. These two processes are actually in the main memory and nobody knows who is going to get selected by the scheduler. Scheduler may select either Krishna or Chitra. But when scheduler selects one process, obviously that process must execute. But there is a restriction imposed that initially Chitra must execute, followed by Krishna. Okay, let us say Chitra will print India. Krishna will print is my country. Okay, when this process Chitra executes, it will print India and Krishna executes, it is going to print is my country. Now you can understand which has to be executed first. But there is no guarantee such that Chitra will get scheduled before Krishna. Scheduler may also go with Krishna because depending on the priority. But these Chitra and Krishna, two processes, must impose self-restriction that they wouldn't execute even they get scheduled, even Krishna gets scheduled prior to Chitra. So for that, what we need to do is, what we can do is, in fact, we can use the semaphores in a different way to construct a synchronization, mechanism in such a way that there will be an orderly execution. There is an orderly execution. How? Let us understand. Simple. A synchronization semaphore will be initialized to 0 initially. Actually, binary semaphore should be initialized to 1. But a synchronization semaphore will be initialized to 0. So, in this CH process, right after it executes a print, what we call India, it will release semaphore S, that is signal S. Then within KR process, before it prints is my country, he needs to perform a wait operation on S. So what will happen? Whenever, Krishna gets scheduled initially as a semaphore S value is initialized to 0, he will get caught in the while loop. Rather, he will get blocked. Actual definition of the semaphore will block any process which finds the semaphore value S is equal to 0. In that light, if Krishna gets scheduled prior to Chitra, he will get blocked on the semaphore S. Because since the semaphore value is not at equal to 1, this will only be equal to 1 right after Chitra finishes her execution. Unless CH process finishes with the execution, this semaphore S value cannot be equal to 1. Even KR process enters into the CPU, it will get blocked on semaphore S. So let us say one fine moment, right after one fine moment, CH process got scheduled and then it performed the printing, right after which it performed signal operation. When the signal operation has been performed, semaphore S value becomes 1 again. Okay, then it is allowed. This KR process can enter into the CPU and can starts its execution. Since semaphore S value is equal to 1, it will be successful in performing wait operation. I hope I made it myself very clear. Okay, so am I clear? Yeah. Any doubts? So far? Yeah. Now obviously process P1 should execute first, followed by process P2. Now process P1, right after the first statement has been finished, it will perform signal operation. Then process P2, before it executes, it needs to perform a wait operation. Then even though process P2 gets scheduled prior to P1, it will get blocked on the synchronization semaphore since it is already initialized to 1. Unless the process P1 gets executed, there is no ever way for process P2 to go ahead with its execution since it will get blocked on the wait semaphore, on the wait operation on the semaphore, right? Yeah, can implement a counting semaphore S as a binary semaphore, as I already told you. And now understand carefully. I am not showing anything. So what I'll do is, I will make it empty to have you people listening to me with a plain mind. Okay? You don't need to read anything or watch anything. Just watch me and what I'm saying. You just need to have your ears all the time focused. Okay? Now the thing is, semaphore, we need to redefine. Since the standard definition of the semaphore is still experiencing the busy waiting. Busy waiting is the biggest problem. Now let us understand something very clearly. First of all, we need to understand a strategy. We will understand one logic through which we will be able to implement the redefined definitions for wait and signal. The thing is, I am a process. You are, some of the processes. You process are executing in the critical section. When you process are executing in the critical section, obviously the semaphore value is not available. When I check for the semaphore value, it is not available. At that time, what I will need to do? Generally, I will be put in a busy waiting. I will be looping around a while loop all the time. So, the problem is, when I am in the ready queue, CPU will schedule me. If I move from the ready queue to somewhere, obviously CPU will not have a look at, is it making some sense or not? Understand carefully. There is a process X. There is a process X, which is already in the critical section. Okay. That means that the semaphore S value is not equal to 1. When the S value is not equal to 0, when another process Y comes to CPU, gets into the CPU, it won't be able to come out of the while loop. It will be caught in the while loop all the time. So rather than doing that, what it can do is, rather than being caught up at the while loop, it may request the operating system. It can request the operating system, Mr. Operating System, please don't schedule me. If you schedule me, that is not productive. As long as the semaphore value is not available, even I enter into the CPU, I can't do anything. I will have to wait on a while loop. I need to wait within the while loop. So I don't want to come to the CPU to simply waste the time. Please don't schedule me at all. Do one thing. Whenever that process finishes with the critical section, at that time you consider me for scheduling. So this is the request will be made by any process whenever it finds that the semaphore value is not available. I hope I made it myself clear. So the moment I enter into the CPU, let us say I got scheduled. I'm checking with the semaphore value, not available. Immediately I'll request the operating system. Mr. Operating System, semaphore is not available. Please don't send me back to the ready queue. If you send me back to the ready queue, sooner or later you will schedule me again. When I come to CPU again, as long as the semaphore value is not available, I will still be in the busy waiting. So I don't want that. Please send me from the ready queue to somewhere else. So this is the request that is made by any process which find the semaphore value is not available. Got me? Let us say there is X process which is already in the critical section. Now there is Y process. Y process found that the semaphore S value is not available. It will request the operating system not to schedule it again anymore. At that time, operating system, rather than putting Y in the ready queue, it will completely block Y. This Y will get completely blocked. I am requesting the operating system to block me. Don't schedule me. Please block me. Blocking means there is nothing. What exactly is blocking? So this operating system will go to the PCB of Y and will change the state of Y from the ready state to waiting state. If a process is said to be in a waiting state, that means that that process is actually waiting for an event. Making sense or not? Yes or no? Any doubts you can ask me right now. I just want you people to be perfect in the semaphore right after this session. So let us say there is a process Y, found that semaphore S value is not available, will request the operating system to block itself. When a process Y has been blocked by the operating system, immediately the operating system will move Y from ready queue to waiting queue. There is a ready queue. Okay. What is the ready queue? A ready queue is just nothing but the main memory. If a process is in the main memory, obviously this will be considered for scheduling. There is a scheduler. If you remember, we talked about a scheduler. This scheduler will always look at the main memory, which is not just nothing but the ready queue. If this process comes back to the ready queue, obviously this guy will get scheduled sooner or later again back to the CPU. No matter what is the use, as long as the semaphore value is not available, there is no point in scheduling this guy who is waiting for the semaphore. So what operating system does is, this operating system will block this Y. What is blocking? Blocking is nothing. Simply, it will shift this Y from ready queue to the waiting queue. Okay. This Y will be moving to one queue called waiting queue. This waiting queue is specially designed for the process which are actually waiting for a semaphore. So, as long as X is inside the critical section, there is Y. There enters Y. It found that semaphore value is not available. Immediately it will get blocked by the operating system. Rather, process Y itself, it makes a request to the operating system, please block me. Then the operating system will block the Y and send it to the waiting queue. Then one more process Z. Z also found that the semaphore value is not available. Immediately Z also makes a request to the operating system. Mr. Operating System, please send me also to the waiting queue. So Z also has been sent to the waiting queue. Similarly, any number of processes, when they found that the semaphore S value is not available, they will request the operating system to block themselves. Since when they go back to the ready queue, the scheduler guy will immediately schedule them sooner or later. When they go into CPU, they are going to consume a lot of clock cycles, right? So now to avoid that, all the processes which are actually has to wait on a semaphore will request the operating system to block them. Subsequently, operating system is going to transfer them from the ready queue to the waiting queue. Okay, so did you on par? Are you on par? Yes or no? Any doubts so far? I want to know. Right after you say yes, I will go to the next subsequent thing. Harshita, Krishna, Anu. I hope you got it. Okay, is it, you responding immediately or busy waiting avoided? Yes, busy waiting is avoided by this approach. Now the thing is, we need to implement this approach. Only we discussed orally. Okay, let me tell you, operating system's job is very simple. Every process will have a PCB. There is a PCB associated to every process. Let us say there is a process X. Okay, process X will have a PCB. What is a PCB? PCB is just nothing but a table that represents the state of this process. In this PCB, the process will have a state, will have a program counter, will have some registers value and some other data. Total data is maintained by the operating system for every process. Every process which is active in the main memory, which is available within the main memory, will have a PCB within the operating system's kernel. So, what operating system does is, every time when a process requests it to block it, immediately the state of the process which requested to block itself will be changed from ready to waiting. Ready to waiting. I am the operating system. You requested me to block yourself. So what I'll do is, I don't turn the world upside down. Simply, I will go to your corresponding PCB in the kernel. Simply within the kernel, there is a PCB. Your PCB. I'll open the door of your PCB. In that, there is a field which is called state. In that state, I will change that state to from the ready state to the waiting state. That means that you are blocked. As long as you are in the waiting state, you will not be picked up for execution by the scheduler. I hope you got it, what is being blocked, right? Yes or no? I think you understood what it is being blocked. Yes or no? So that is about blocking. I explained this. Now let us understand. Yes, each semaphore, there is an associated waiting queue. For every semaphore, there is an associated waiting queue. Okay. Every, semaphore will have two things. The first one is value and a pointer to the next PCB in the list. What is this? I'll tell you. In order to redefine the semaphore's wait and signal operations, first of all, we need to define something called a structure with a name semaphore. Let us look at the lower portion of the screen. If you want to redefine wait and signal to be completely free from busy waiting, initially, before we go and define wait and signal, we need to define one structure with a name semaphore. Here, typedef struct with a name semaphore. This semaphore structure will have an integer value and a list of the processes that are blocked on that semaphore. List of the processes that are blocked on the semaphore. Once again, stay focused. Every time when you want to redefine the semaphore, you need to define a structure for each semaphore. Every semaphore structure will have two entities in it. The first entity is semaphore's value. Second entity is a list of the process, a pointer to the list of the processes that are blocked on that semaphore. So right after which, I will take you people to the definition of wait and signal. Let us have a look at the wait operation of the semaphore. In this wait operation, what we are doing is, we are not using while condition at all. We are not using the while condition. Rather, what we are doing is, let us say initially s value is equal to 1. Directly we are decrementing the value. S value is being decremented initially. Value of the semaphore is getting decremented right now. So let us say the value will become 0. Then we are going to check if s value is less than 0. Obviously now it is not less than 0. For the first process, s value cannot be less than 0 since initially decrement has been performed. Once after you perform one decrement, obviously 1 will become 0. So for the first process, s value is not less than 0. So it will come out of this, it won't enter into executing the statement. Rather, it will go and execute its critical section. Let us say one process, first process, initially it performs s value minus minus, decrementing the s value, right after which h value becomes 0. Then this if condition will not get satisfied, then it will enter into the critical section. Now there comes one more process. That process, when it performs s minus minus, this s value becomes minus 1. Anu, your doubt. Can the semaphore value ever become negative? I have your answer right now. Under the standard definition, semaphore value can never go negative. But in the redefined definition, redefined wait and signal operation, wait operation especially, semaphore value can go negative. I will talk more about this negative value. Hold on for a while. Okay. So for the second process, obviously, semaphore value has been found out to be minus 1. So this if condition has been satisfied. While this if condition gets satisfied, what will happen is, immediately, this will be added to S list. Okay. How to implement this list is one more problem. Rather, one more design implication. This list can be implemented by using a queue data structure. Okay. You know what is the queue data structure? In a queue, we will have head, we will have a tail, right? Obviously, this list will be a linked list. So, this head will point to the first PCB that is actually waiting for the semaphore. Okay. So, immediately, let us say first process which finds that the semaphore value is minus 1 will be added to this list. So, this list queue is going to point to first PCB and tail will point to the final PCB. Now, we can maintain the list as this way. Did I make myself clear? Yes or no? That means that this queue is exclusively for semaphore. The total number of PCBs here will state the total number of blocked processes on that semaphore. Did I make it myself clear or not? Yes or no? Other process blocked. Yes. All the other integer value and queue. Yes. Integer value and queue. Queue list of PCBs blocked processes. Absolutely. You are spot on, Chitra. Okay. Yeah. Now when it comes to the signal operation is fairly simple. Let us see, when the first process comes out of the critical section, it needs to perform signal operation. In the signal operation, it will increment value. Right after the incrementing, if the value becomes 1, understand carefully, this is very important. I don't want you people to, I don't want to put that. I don't want you people to be, inactive. I just want you people to be very active indeed in order to understand this. See, I am the process that is coming out of the critical section. When I perform signal operation, I found that right after incrementing, the value is equal to 1. If the value is equal to 1, no processes are actually waiting. But if the value is still either equal to 0 or less than 0, that means that a few of the processes are still waiting for the semaphore. Whenever there is a process waiting for the semaphore, I need to invoke those processes back. Did I make myself clear? Sir, no. Let us say there are several people, 13 people watching. In the 13 people, I am the process that enter. Remaining all 12 people blocked on the semaphore. When I come out, what I need to do is, I need to invoke at least one of you process, right? In order to invoke one of you process, what I'll do is, I will execute a wake up system call. The earlier process which has got blocked, executed block system call. I think I missed this. Any process which want to block will have to execute a block system call. The block system call will transform this process state from ready state to the waiting state. So at that time, it cannot be infinitely in the waiting state. Sooner or later, it needs to bring itself back from waiting state to the ready state. How that event is going to happen? Whenever the first process that enters into the critical section, when it is coming out, when it releases the semaphore, still finds that the semaphore value is still less than or equal to 0, needs to wake up at least one process. So the first process, when it performs wake up operation during a signal execution, this wake up system call will exactly invoke one random process from the queue. Is it making sense or not? There are several processes. Let me tell you. This is a queue. X, Y, Z, A, B, C, D. All these processes are waiting. Since myself, AN, already in the critical section. And a semaphore, these processes are waiting for a semaphore S. Okay, so this is, these people found that semaphore value is negative. Got me? So negative meaning it is -1, -2, -3, -4, -5, -6, -7. These people, they reduce semaphore to -7. That means that a total of 7 processes actually waiting. Anu, one more point here. Here the negative magnitude is the total number of processes that are actually waiting for the semaphore, right? Waiting to enter into the critical section, right? Under the standard definition of the semaphore value can never go negative. But here, the negative magnitude states that the number of processes are actually blocked and waiting in the queue. The moment I come out, I need to invoke at least one of you guys. For that, what I'll do is, I will perform a wake up system call. When I execute a wake up system call, the operating system will invoke exactly one process from the queue, this waiting queue. One process randomly. It may be A process, it may be C process, it may be X process. But one process which has been blocked for that semaphore will be invoked. Okay, so that is what the wake up operation. Any doubt so far? Any doubt so far? Now, very good, Harshita. Now stay focused. Now stay focused. Let us say there are several things that are needed to be clarified. Tomorrow, when you watch or rewatch this session again, I don't want you people to be any doubts, to be getting any doubts at all. For that, I will, forethink those doubts and I will explain from your point of view. Let us understand a few things here. This is a waiting queue. Okay? This is a waiting queue. There are several processes. A, B, X, Z, C, D. These are in the waiting state. Okay? Now let us understand. One process AN is in the system. The moment AN leaves the system, he is going to execute a wake up system call. This wake up system call exactly is going to wake up one process. What is waking up? Waking up meaning one process will be randomly picked up and it will be sent back to the ready queue. Okay. Now when a process is sent back to the ready queue, it can be taken into account for scheduling. There is a scheduler guy again. The scheduler obviously will take this, X into consideration for scheduling. It is not guaranteed that immediately the moment X has been woke up, it will directly enter into the CPU. Doesn't mean that. Only X will get transferred from waiting state to the ready state. That meaning waiting queue to the ready queue. It doesn't mean that X will get immediately scheduled after AN. It may get scheduled, may not get scheduled. I hope you got the point. Wake up operation meaning it is only can perform, rather can transfer one process which is already in the waiting state to the ready state. That's it. I hope you got it. Now, the very important things that we need to understand at this session. Stay focused and understand. What are the criteria, madam? Just tell me. The criteria you type. What are the criteria for any solution that needs to satisfy? You talk about any solution. Any solution that you want to propose must satisfy 3 criteria. Tell me what are those criteria. Let me see how active you are. Harshita, Chitra, Anu, Krishna, Chanchal, I want you people to put the criteria. What is the first criteria that must be satisfied whenever we propose a solution? I will wait. I will wait as long as you people put into waiting queue. From waiting queue to the ready queue. Not from ready queue to the waiting queue. When block executed, when block system call get executed, process will be sent from ready queue to the waiting queue. When wake up gets executed, one of the process will get randomly selected from waiting queue and sent to the ready queue. Now tell me, what are the criteria that must be satisfied by any solution? Arey, tell me, I am just waiting. The criteria, okay, fine, did you forget? Fine. Let me write it. The criteria that are needed to be satisfied by any solution is mutual exclusion, bounded waiting, and progress. Yes or no? These must get satisfied, right? Including semaphore. Semaphore is no exception. When we use semaphore, that means that it must satisfy all these criteria. Otherwise, we don't use the semaphores at all. Yes or no? I'm waiting for your answer eagerly. Or else, are we done? What is process ID? What is process ID? Yeah. We need to satisfy mutex, and we need to satisfy bounded waiting, and we need to satisfy progress. Any process, any solution must guarantee all these 3 things. Otherwise, we don't use. Now the thing is, mutex will of course be satisfied by the semaphore. Now we should see if the bounded waiting is getting satisfied or not. Obviously, bounded waiting is not being satisfied at all. Bounded waiting at a definition level is not being satisfied. Simple. If the semaphore value S is equal to 1, obviously any process can make this semaphore S value equal to 0, can enter into the critical section. Here, how to satisfy the bounded waiting? In order to satisfy the bounded waiting, I will tell you one simple rule. Write it down on a paper. We are maintaining a queue of the process which are blocked on the semaphore, right? You maintain the queue as a FIFO queue. I hope you got it. In order to have the semaphore satisfying the bounded waiting, anyhow you implemented a queue. In this queue, several processes are waiting and blocked on a semaphore. A, B, X, Y, Z, C. These processes are waiting for a semaphore. Now, current process which is in the critical section, when it executes a wake up system call, this wake up system call can randomly pick up one process and send it into the ready queue. But the problem is, what if this random process just left the critical section? Obviously, starvation will still happen. So, in order to avoid that, you maintain the queue as a FIFO queue. If you maintain the queue as a FIFO queue, then bounded waiting is guaranteed to be satisfied. Simple. This wake up system call can only wake up the first process in the queue. Yes or no? Got me or not? Hi, Aarti Shagal. Very good evening. Yeah, yes, sir. Really make it yes, sir, it's making sense. We need to we need to make sure that semaphore satisfies bounded weighting. And followed by progress. Progress will anyhow be satisfied. We don't need to talk much about the progress, but only the thing is bounded weighting satisfied? No. At the definition, no, it is not satisfying. What you can do is, you implement the list with a FIFO order. If you can actually follow the strategy of FIFO, only first process that is actually waiting for the semaphore will be woke up first, followed by the second process, followed by the third process, followed by the fourth process. That way, you will be able to easily implement bounded weighting. Did I make it myself clear? Yes or no? Yes, no, Aarti? Hi, Tushar. Where are you? Very good evening. Okay. So in order to satisfy the bounded weighting, in order to have the semaphore satisfying the bounded weighting, what we need to do is, we need to implement this weighting queue with a FIFO strategy. Then bounded weighting will get satisfied. So this is thing must guarantee that no two processes can execute wait and signal. This is atomicity. One more guarantee that we need to provide is, wait and signal will have to be performed atomically. If one process is performing wait operation, no other process should be allowed to access wait and signal. Similarly, signal operation also, whenever one process is performing signal operation, it should be provided access to one and only one process. So what we need to do is, since semaphore is a small integer, it is neither the implementation of the hardware nor implementation of the software. It is a semaphore. S is a programmer's variable. So what you can do is, understand carefully. Critical section, before you enter into the critical section, you need to perform wait and signal operation. Okay, so I will rewrite it in order not to overlap. Critical section must be protected by wait and signal operation. In order to make sure this wait and signal operations are performed atomically, what you need to do is, you need to protect this wait operation and signal operation by using either test and set lock or again mutex locks. I hope it is making some sense right now. See, busy waiting is not completely eliminated. Rather, of course, in order to make, see, semaphore S value is also critical section, right? Since S is also an integer, S value may be accessed by several processes at the same time. In order to have this S value accessed by only one process, we need to protect this wait and signal operation by using either mutex locks or the test and set lock. Now at this point, what happened is, this busy waiting has been moved from the critical section to the entry section. It makes every sense. Busy waiting, if it is for the complete critical section, it will take a lot of time. But in order to only protect wait and signal, a process need not be in for much busy waiting, for only one clock cycle or two clock cycles, since semaphore S is a single integer, single variable. Any process which is accessing the semaphore, within one clock cycle, it will be able to access the semaphore and update it. So busy waiting has been shifted from what you call critical section to entry section. So this is how semaphore also guarantees what you call the my mind is going blank. Is it making some sense or not? Thank you so much. Thank you so much. Yeah. This is the way we also guaranteed the atomicity. Wait and signal operations are performed atomically. For that, in order to protect these wait and signal operations, we need to use test and set lock or mutual exclusion locks, mutex locks. Let me tell you, yesterday I showed you something, that all the modern days operating systems or the modern days processors are providing the programmers with the locks. You need to use some or the other locks to protect your wait and signal. If you can protect your wait and signal by using the locks that are being provided by either the hardware developer or the software developer, you will be able to achieve everything, every goal of the semaphore. Here, semaphore satisfied. Obviously, mutual exclusion, semaphore satisfied, bounded waiting. Let me tell you how the semaphore satisfies the bounded waiting. Simply by making the waiting queue, implementing the waiting queue in a FIFO order. We are going to define the list as a FIFO list. You can use the data structure, right? So if you can maintain the list in a FIFO order, then bounded waiting will get satisfied. Obviously, progress got satisfied. One more constraint is wait and signal operations must be atomic. When wait and signal operations are being performed by some process, that should not be accessed by any other process. In order to have it atomic, please protect your wait and signal operations by either mutex locks or TSL locks. Since TSL and mutex, by this definition themselves, they say that, they assert that, they admit that they are atomic. So everything is satisfied by the semaphore. Wait and signal are being executed atomically. Okay, atomicity has been ensured, followed by all these criteria are also satisfied. So semaphore satisfies everything. Now, I don't want to overload you people. I just want to explain a lot of things on the semaphore, but this is fine. What I'll do is, I will take a separate session on the problems that we're going to face when we use the semaphores in a wrong manner. If the implementation part is not correct, semaphores are going to make your life miserable. So for that, what we need to do is, we will make sure that the semaphores are implemented in a proper way. So for that, I will take a separate session. This is fine as far as my knowledge is concerned. I hope this is pretty fine for today's session. I can't overload you people. So what I'll do is, for exactly explaining how semaphores can make your life miserable if you implement them wrongly, I will take a separate session. Okay, I'll talk about the bounded buffer problem. I will talk about any other synchronization problem, how it is going to get protected by the semaphores in the next session. So thank you so much. That's it for the session. I hope you enjoyed the session. Once again, before I sign off, like and share the session and subscribe to this channel if you haven't already yet. Anil Prasad Surampudi signing off. So I'm giving you 2 minutes to shoot any more doubts. But sir, 2 process implement hota hai kya? Of course, 2 process you can implement semaphores for any number of processes. Semaphore is just not only for 2 processes. You can implement, you can protect a critical section for n number of processes. There is no restriction at all. Anything else? Number of processes. Sir, what? Cache? That is white cache, black cache. It is not right now. It is completely out of the context. That's altogether a different ball game. I'll talk about that later. Not right now. This session is for semaphore. When I come up with a CO, that too, cache memory access, I will explain you what is that, but not right now. Okay. Very good night, Tushar. Chitra, where are you? You are there. Chanchal, Aarti, Krishna, where is Krishna? Yeah, that's it from my side. Anil Prasad Surampudi signing off. Thank you so much.